Okay, good morning if you're working at the morning, good evening if you're watching it at evening. So this is a second video which complements the LAB11. I will try to demonstrate how to do absorption spectra in case we explicitly treat electrons with spin projections alpha and beta. It is called spin polarized DFT. It was referred to as unrestricted DFT or unrestricted Hartree-Fock when we did it with Gaussian. And the model that we are looking at is titanium hydroxide molecule, 1 titanium and 4 OH groups. This molecule has singlet configuration as a lowest, as a ground state, and in the triplet, the gap is above 4 electron volts. It is in UV, and upon creating a triplet, this configuration may change. So just as a reference point, here is the spectrum of this molecule in the singlet configuration. Right now, we are going to see how this image will change if we go into the triplet configuration. So on the local computer, I will go to the pre-made directory triplet meter opt. I will use at the end of our meeting a string to transfer files from Photon. Right now there is nothing, but I have created a directory on Photon in my subdirectory where I intentionally plan to transfer files that I will create right now. And on NERSC, I'm going to triplet neutral OPT L, so that it doesn't block our way. So there I was looking onto a model of titanium hydroxide, so 1 titanium, 4 OH groups. And before going forward, I did optimize the structure. So I requested 60 steps of optimization. So the geometry is optimized, and typically it serves to reduce the gap. Now, first, there is a manual. So more tilde b device in new. So I'm blindly going to follow these instructions because they are correct. I should admit I typed in myself just in case my memory doesn't serve me well. So first step is to create file input overlap. This file just instructs which range of orbitals we are going to explore, and it lists underscore. So I can do from 6, from 6 to 6, and then number 1 is just service number. Escape W2. More input overlap. Now, the step number 2, if you are running it for the first time on in your session upon login, you may need to change to swap modules. By default, NERSC uses the environment, the libraries for Intel Fortran compiler, and what we are doing was compiled with GNU public Fortran compiler. So I need to swap these modules. If I try to swap them right now, it will show an error because I already did it. Okay, next I want to extract the list of orbitals. So it shows string is found, which is okay. I'm typing ls-t, and I see energy pop and energy pop down. Energy pop. So it is a list of orbitals. If I want to later do those, I can states even can copy. So it is the file, it is a list of orbitals, and it is extracted automatically. We do not need to go into the outcar manually. It just gives this list of orbitals starting from requested first orbital, ending with requested last orbital. Since it is a triplet, compared to what we had before in the previous video, compared to a segment, in the alpha spin, which is an energy pop, electron spin up, we have orbital number 17 occupied. Well, before in the ground, everything up until 16 was populated, and after it was empty. Now we are populating one more orbitals in the alpha and one less orbitals in the beta. But the fundamental gap is still between the 16 and 17. Okay. Now let's look more down. So it is the second list of orbitals. Now 16 is empty. There are 0 electrons, but fundamental gap is still between orbital 16 and 17. So because we borrowed one electron from here, from orbital 16 in spin down, and promoted it to the orbital 17 in spin alpha. So let me show the manual once again and explain what is going on. So next we are going to extract so-called oscillator strength files. So oscillator strength files show intensity of optical transitions between each pair of orbitals. This oscillator strength, this intensity of transition, is absolute value squared, summation of absolute value squared of all transition dipoles, matrix elements of transition dipoles. And here we explicitly take into account the spin. This, we are going to run these two scripts, oscillator strength up, oscillator strength down. Each of these scripts uses two input files. Energy pop, either without underscript or energy pop down, and wavecar. So wavecar contains orbitals, wave functions, and energy pop contains orbitals. So we pick one by one pairs of orbitals, take their from wavecar, the energies from energy pop, and compute rates of transition upon optical excitation. So we do need to make sure that that the wavecar is not empty, that it is available. If I look into my in-car, there is a L wave equals true. So wavecar is being created. Just make sure that if you try to compose in-car yourself by hand, if this line is forgotten, wavecar can be missed, and then this spectrum will not work. Okay. Let's just run this scripts. Run. Ready. Minus T. Okay. As a result, we have oscillator strength. This is oscillator strength for spin up. we will later rename it. Now, let's run the second script. Step 5, Control C, Control V. It is done once again. LS minus LT head. We have oscillator strength down. Now, if we look on the menu once again, the next step is to fix the namings. We will call what was oscillator strength for up. We will explicitly add a label oscillator strength up. Now, if you look inside the oscillator strengths, we will see that the structure is as follows: initial, final index of orbital, oscillator strengths, transition energy, initial and final population, and then 3 components of transition dipole. So you see this file shows from 0 to 0, means from unoccupied to unoccupied, and from occupied to occupied. If you look long enough, if you scroll through this file, let's do it. Strengths. If we scroll long enough, we could be lucky and we can identify that there are few transitions that starts with occupied and end with unoccupied. Their transition energies will be smaller, and their oscillator strength will be smaller, and transition energies will be bigger. So for optical absorption, we need only such transitions, because it is what happens in linear absorption. System from ground state is all occupied are below up, transferred up. So we need to extract this occupied to unoccupied lines transitions from this file. Make sense? Let's look through the manual once again and see. So here is the command that parses, extracts the record that contains 100 to all zeros from one file to another one. So now if I look into this new create file os up, you see it has transitions only from filled to empty. Okay. Now I need to do the same for spin down. If I do ls minus ot head, I observe there are 2 new files created. And here I'm going to follow next little steps from the manual. I want to combine these 2 files that corresponds to optical transition with spin up and spin down into a single file. So cat stands for concatenate. And if now I check the files, there is a file oscillator strengths, which is twice as bigger than os up and os down. And it has all transitions with spin off and spin in. So manual stops at this point, but now we pick up our previous skills and we are going to apply a way to convert discrete list of transitions in the oscillator strings into continuous spectrum strings to 18. Now I'm typing in spectrum in P3 number of transitions to 18. We start from positive number close to 0 we end at least in 8 to cover some UV. Each line 005, comma. Originally it was 16. Later on you can, it doesn't change how the file is computed. It's only for normalization. Now I have ls-t here, and I have file spectrum. So the second line has transition energies in electron volts. Third line has intensity of absorption, and first line has transition energies in converted into wavelengths, transition wavelengths, nanometers. If you start too close to 0, it's not enough digits, so maybe we can, without any loss, remove first 5 lines. DD, escape W. Okay, now there are several scripts that convert spectrum file into graphical information. So I'm just typing GNU what. It executes this little script. I do see that there is a file sp1.ps. I want to convert it into PDF. And at this point, I want to transfer this PDF file. I better type it from scratch. SCP is everything that ends with PDF. From here to user server for phone. And I help my memory by dropping this string. So it is pre-made directory for triplet neutral optimized. So SP1 file is transferred. In the local computer, transfer this file. I'm going to the EF viewer, going to the directory triplet neutral optimized, SP1. So this spectrum is very different compared to what we had before. So previously, the features started when we had a singlet. It started at about 4.5, right? And everything below in the visible range was empty. Here we still have this 4.5 transition, but in addition, there are several peaks in the visible and infrared range. So what is an explanation for these peaks? So if you look on the density of states for this model made before, we see that from occupied to unoccupied, we can have transitions with very small transition energies, like from the bottom of the conduction band with spin alpha and higher up, right? If, in addition, beta transitions, we can have transitions from the from anywhere in the valence band to the top of the valence band. So these small transitions will have energies in the infrared and visible range, and they are adding, they contributed to make a signal visible. So if we know how to convert titanium hydroxide into triplet state, it will immediately become colorful. So transparent molecule will become colorful. Later on, we will try to apply this to different metal organic systems as a part of your project, but it is a most important observation. If you are in a rush, you can stop watching now. So formal part of this instructional video is done, and I'm going to record further and show two extra. First, how to redo the spectrum as a function of wavelengths, which is typical for experimentalists. And second, how to decompose the spectrum onto partial contributions from spin up and spin down, just for a little bit better analysis. But again, I'm not sure that it will be ever required. It's only for curiosity. Okay, which scripts do I have? So GNU probe SPE nanometers. Let's watch it first and then run more. So it plots spectrum, but on the x-axis, before we plotted, x-axis was chosen as line 2. Now it is column number 1, which has transition energies in nanometers. Here I set x range in a very broad range from UV to infrared, but optical is only from 400 to 700, so it will show all ranges. And the file will be sp_nn for nanometers. So let's run this script. We convert discrete into continuous. It will visualize the spectrum. So sp_nanometers. Yes to pdfwr SPE. Now we have the PDF file. Let's transfer it to the photon. Oh, I mistyped it. And on the local computer, I am downloading everything and files ended with PDF. And now I'm going to look how the spectrum will show up in the as a function of wavelengths. So what I'm going to focus here, and if I would be doing the research for hire, if someone hires me, right, or research for publication, it is very important to label each peak. Otherwise, it is not possible to speak about them. So I would copy it into PowerPoint and just add labels. If you look to the electron volts energy, so 4.5, the first fundamental gap transition, is converted into transition here about 300 nanometers. So everything in this range is here up to 300 nanometers. The peak that I'm showing with marker is fundamental gap, and other peaks in the visible and infrared range are so-called intraband transitions. So interband, it is from valence to conduction, from occupied to unoccupied originally. Now those are inside the band. And we see the lowest peak is not covered. We need broader range of infrared to show the last peak. Okay, this is end of the first little addition, and now I'm going to second little addition. I'm going to decompose this spectrum as function of transition energies onto partial contributions from spin up and spin down. So back to NERSC. I'm going to use this script, beam the probe spectrum spin electron volts. So here I need to have total complete spectrum and partial spectra for up and down. Complete spectrum is ready, and for partial spectra up and down are not yet ready. I will quickly compose them. So move spectrum into spectrum complete. Done. Now I'm removing was strings and recreating cat OS up bigger OS WC OS strings 16 and converting the oscillator strings into discrete into continuous. To 16 going, okay, let's do a little bigger so that 8 going 005. Done. Here. So we have spectrum. Now we need to rename, move spectrum into spectrum underscore up. So I'm doing it in order to practice this line, to plot 3 spectra together in one panel. Now I'm removing later strings once again and recreating cat OS down, bigger OS. No, this way. WC was strings 220. Why? There are more transitions. I can't believe it because sometimes because form is different, but let's double check once again. Remove oscillator strings. 1, 2. WC was strings. Yeah, 220. Now let's convert discrete into continuous. So right now, we do have spectrum, but it is spectrum for transitions of spin down or beta spin. Let's move spectrum into spectrum down. Now we have all 3. So I'm going to plot them together by running this little script under GNU plot. As a result, I'm getting this SPE spin underscore VPS. So PS to PWR SPE spin checking. There is a new PDF file, and I'm pushing the arrow up button because I'm lazy to retype this transfer command. Yep, here, transferring everything ending with PDF. And now going to the local computer, transferring from photon to here. And let's look how this spectrum is looking as function of in decomposed way. Okay. I believe this is very important. So what we had before, total spectrum, and here we have a repartition spectrum. The relative height of the peaks is slightly modified because it renormalizes when we do when we go from discrete to continuous. It adjusts things so that the area and the curve and maximal height are normalized, but the complete spectrum is the blue or cyan line. In a way, how I did it, it will be halfway between purple and green. So it is cyan, blue, sky blue is equal at each point is equal purple plus green divided by 2. So it's about halfway. So the fundamental peak at 4.5 is contributed by spin down only. So if you look on the DOS, it means transition of this spin down from top of the valence band to the bottom of the conduction band. It will be this transition. Then if you go into the visible range, there are several transitions from 1.5 to 3.5 that are contributed by spin up. If you look on the spectrum for analysis, it means it will be transitions from this electron at the top of the conduction band higher up into conduction band. You see there are noticeable big offsets between for transitions, and they will contribute to absorption in the visible range. And then there are transitions below 1.5 in the infrared range are contributed by, again, by spin down. So in the valence band, the states are more sparse, and transitions from nearest states to this empty state are have quite small energies. So this analysis is maybe too detailed for the course, but if you are including spin polarized spectra into your professional research, it can be reasonable to include such analysis. So maybe after I'm done with the video, I will summarize all created figures into one PowerPoint and share it with everyone. Okay, I'm going to stop the video and share it very soon so that it can be used as a preparation towards presentations.